Good morning, friends. Hope you all are doing well. In this video, we're going to go over surface integrals. So to start, let's look at the differences between line integrals and surface integrals. So line integrals evaluate functions along a one-dimension curve, and surface integrals extend the concept to two-dimension surfaces in three-dimensional space. So line integrals, one-dimension curves, surface integrals, two-dimension surfaces. And parameterization is essential for representing surfaces in these calculations. So if we look at the formulas that we have here for line integrals, we have our scalar form where your R of t is what parameterizes the curve C. And then here's the form for vector field. And for surface integrals, we have our formula for a scalar field, and here ds accounts for the true surface area of S. And for our vector field, you have your n, which is the unit normal vector. So conceptual differences: line integrals calculate values over one-dimensional path, and then surface integrals generalize this to a two-dimensional surface, which sums up the contributions over a curved or flat region. Okay, so before we get into it, we're going to do a little overview of the concept of surface integrals. So key things to note, starting with parameterization of a surface. Which represents a surface S as vector u v, where u and v are parameters. So for example, for z is equal to fxy, we would write it as that. Okay, so next we're going to look at the differential surface area. Where the surface element ds is derived using the cross product of the partial derivatives. Okay, so in terms of applications for scalar fields, you're able to use them to compute things like heat flow, surface area, or the total field magnitude over a surface S. And for vector fields, you can use them to compute flux through the surface S. So a little explanation. The cross product of the partial derivatives gives a vector perpendicular to the surface where its magnitude represents the area of the infinite patch of the surface. And by integrating f xyz over these patches, it sums up the total across the entire surface. So we're going to look at some examples to make sense of that, starting with this surface integral. So we're given x is equal to u cosine v, y is equal to u sine v, and z is equal to v. The first step is to parameterize. So we're going to do that by finding the partial derivatives. For both u and v. Okay, so the reason why we parameterize is because direct integration is harder with higher dimensions. So by parameterizing, it simplifies the process by mapping our 2D region, which is defined by u and v, onto a 3D surface. And then from there, we're able to find the surface element ds instead of the integral. Okay, so now that we have the partial derivatives, we're going to find the cross product of the two. So cross Okay, next we need to compute the magnitude of the cross product. So it's supposed to be a parenthesis. So you get 1 plus u squared. And so the next step is finding ds. Which is equal to what we just found, and then du dv. Oops. So we're looking now at the formula for the surface integral. Here, I'm going to plug our values in. So for the surface integral, 1 plus u squared du dv. And we're going to stop there. So that's what we get for that one. So let's go ahead and try another. Okay, so I cut out, but let's try this next example here. This is what we're given. And in this case, since z is equal to gxy, the surface is parameterized by this, okay? Okay, and so in this case, your x and y are the parameters. So we are going to parameterize using that in the same way that we did in the previous problem, but with x and y. Okay, so next step after computing those partial derivatives is to find the cross product. So we're going to cross those two, which is the same as there's a different way of notating this, which I think is what I did earlier, but it's the same thing. So okay, so let's now find the magnitude of the cross product. Just plugging those values in. Okay, so now we can set up our integral. Dx dy. Okay, so here this here is your ds, and we're going to stop here for that one as well. So let's do 2 more examples where we follow through with the integration. And yeah, okay, so for this next example, we are given f x y z equal to z. We're also given that the surface what am I doing? Okay, the surface is given by z is equal to 1 plus x. And for c, we're also given that x runs from 0 to 1, and y runs from 0 to 2. Okay, so I'm gonna write my form here. Gxy, which is equal to 1 plus x. And here the surface integral becomes, we're told that y runs from 0 to 2, and then x runs from 0 to 1. Take my rad 2 out. And I realized I don't have a video on double integrals, but essentially this is for your x, so you integrate this first, and then what you're left with you integrate for y. So right now I'm working on the inside there, and so when I integrate, this is what I get, and then when you evaluate, it would be from x equals 1 to x equals 0. So I'm gonna plug 0 and 1 in. Simplify the inside. And then now integrate with y equals 2 and y equals 0. Okay, so that gives me 3 rad 2. I have here 2 visuals from ChatGPT of the same problem. So to connect the problem to this visual, the plot shows the surface z is equal to x plus 1 over the bounds of x and y. So x controls the slant of the plane, increasing z as x increases, and y stretches the plane along the y-axis. We can also see the interval that they're evaluated on. You can see y from 0 to 2 here, and then x from 0 to 1. And so the integral sums up the values of f x, y, z equal to 1 plus x across this surface, which is scaled by ds. And the final value, 3 rad 2, represents the accumulated z values over the entire surface. So that's that, and let's do one last example. So for this one, we're asked find the surface area of plane z is equal to negative x inside x squared plus y squared is equal to 4. So from this, we get that our radius is equal to 2, because the square root of 4 is 2. And we're going to start the same way. Here we have r and r theta. So I'm going to draw a picture to try and illustrate this. Two radius r, x, and y, and you have your angle there. And this is on a plane. Okay, so my x value is going to be r cosine theta, y value r sine theta, and then my z component, which is equal to negative x, so negative r sine theta. As for our domains, r is valued between 0 and 2, and theta is between 0 and 2 pi, because it's a circle. So to find our surface area, evaluating from 0 to 2 pi for theta, and then from 0 to 2 for r. The cross product of the two, dr d theta. So let's go ahead and compute those partial derivatives. Y, z, hold up, muscle memory, okay. And then next we're going to cross the two. So again, we need the magnitude of the cross product. I'm gonna set up our integral. R equals 0. Okay, so that's what you get for that. And once again, I have some visuals. So let me just move this around. Okay, so here's the visualization of the surface defined by the plane z is equal to negative x, restricted to the region inside the cylinder, however you want to think of that. The cylinder x squared plus y squared is equal to 4, where the radius of the circle in the xy plane is 2. And so we have the circular base, x squared plus y squared is equal to 4 projected onto the slanted plane, z is equal to negative x, which creates the surface to be analyzed for its area. So, okay, I keep cutting out, but that's the last example that I have. So that sums up this video. Formulas to remember is your scalar surface integral, your differential surface element, which is here, and then also the vector surface integral for the flux there. So that's it for this one. I'll see you in the next one. Bye, friends.